All right, folks, we're looking at chapter 2, which deals with atoms, ions, molecules, nomenclature, quite a few things, but it's actually the basics of putting molecules together from atoms themselves. All right, to start with this, we're going to actually start with what the nature of the atom is. Now, Dalton was the first guy who came up with what we actually accept now as the closest thing to our current atomic theory. This is his 5 initial postulates. They were revised in his lifetime, but for the most part, they're still standing exactly pretty much right where they are. All right, so his first one, all matter consists of atoms. 2, atoms of one element cannot be converted into atoms of another element. 3, atoms of an element are identical in mass and other properties and are different from atoms of any other element. 4, compounds result from the chemical combination of specific ratios of atoms of different elements. And 5, atoms are neither created nor destroyed during a chemical change, but are instead rearranged to yield substances that are different from those present before the change. All right, we're going to look into these so we can actually analyze the mistakes that were in these or the incomplete aspects and then modify them into a more relevant to today's atomic theory. All right, the law of constant composition was what gave Dalton one of his first postulates. Now, this was a study done long ago by this French guy who was able to show that no matter where he obtained calcium carbonate, whether it was actual limestone or from coral, he found the exact same percent composition of calcium, carbon, and oxygen. And it didn't make any difference whatsoever where the source was. So he decided, or at least he thought he had figured out, that that constant composition was required. Now, what threw people a bit for a loop, there were other forms of molecules that were different than calcium carbonate. They had the same atoms in there, just doing different ratios. One of those type of examples that we can study now and that Dalton had looked at was copper chloride. Turns out there are 2 different copper chlorides. There is a copper chloride that's green in color and a copper chloride that's brown when it's dry and turns blue if it gets exposed to any water. And while it doesn't look wet when it gets blue, it just actually kind of like changes color. It'd be a great humidity checker here in Florida because your brown crystals turning blue would be kind of obvious. But here in Florida, it'd be blue all the time because we're way too humid. But when we were looking at this, early scientists, they wanted to figure out what was going on. And looking at these masses, it didn't make any sense. But if we look at these 2 and do a little bit of math, we see that this one is actually twice that one. So for whatever's going on, that brown crystal must have twice as much of chlorine in it as the green crystal, which is why the mass is twice. All right. But when Dalton studied multiple molecules like this, he actually found that whenever he actually was able to break it down to those masses like that, he found out that they were whole number ratios. They were never fractions. It was always exactly double or exactly triple. So that gave him the idea that atoms were combining in whole number ratios. Okay, so let's start looking at what the atom is. The very first idea that Dalton was dealing with and had to include into his postulates was J.J. Thomson's study of cathode rays. Now, think of these as early old television tubes because that's kind of what these are. So we run an electrical current across 2 different pieces of metal or anything conductive in a vacuum tube, and these cathode rays come out. And if you run them through a magnetic field or electrical charge, you can guide where they go. In early televisions, that's what we did. They just would bend that line, and they're hitting little dots on the surface here that are red, blue, and green, and they drew a picture. But back when we're talking about this long ago, this was an early type of light bulb because they would just glow on a white hue and get it to glow. All right, neat and all, but what are those particles? That's what these early scientists want to know, what the cathodes themselves are. And they found out that they are smaller than any atom, and size-wise, roughly 1/1000th of a hydrogen atom. So very, very tiny. And the other thing that they found, it didn't matter what the conductive material was. Any metal produced the exact same cathode ray. All right, so they know it has a mass, about 1/1000th, and they knew it has a negative charge. So it's something very, very small. Nowadays, we know that a cathode ray, these are actually just electrons. They're just coming off really, really fast. And they're coming off because of that charge difference. Okay, to figure out more about the electron, this guy, this American, Robert Millikan, used an oil drop experiment to figure this out. So what he does here, inside this upper chamber, and think about this as mostly vacuumed out, we're going to perfume sprayer. He's using a perfume sprayer because it gets a much more fine particle, and he's just squirting that into this upper chamber. Now, separating the upper chamber and the lower chamber is two little plates, or this little plate right here. Right dead center of it is one little tiny, tiny, tiny little hole. And what's going to happen is one of these drops is going to come through and fall. And Robert Millikan is going to look through his eyepiece and time how long it takes to fall and figure out a speed for it. And then what he's going to do, charge up these plates and bombard these droplets with X-rays, which are just powerful enough to knock electrons off of the drops. Well, if an electron's knocked off and I charge this plate negatively, that droplet's going to fall faster. And he actually timed that and related it to the charge. So basically what he figured out was the charge of each one of these drops. That's what's written over here. Now, if you notice, these aren't all the same value. The reason that is because an X-ray source is pretty darn powerful, and these are little tiny droplets. He was knocking off more than just one electron, and that's what's happening here. There is the smallest one right there, and what he needed to do is figure out if it goes evenly into all these, because he knows it's at least one electron, but if it was 2, then the actual charge of an electron is 0.8 times 10 to the -19 coulombs. So really what he does is look for the smallest, and then figures out if it goes into each of them evenly. He's looking for the common multiple of all those. And it turns out that is the actual charge. D was a droplet that had just a single electron it knocked off, and that is the actual charge of an electron. Okay, so early 1900s, theory of what the atom looks like. Now we have two competing theories. Dalton was thinking this. Now this is a British, they call it plum pudding. We might call it a raisin bagel biscuit, something like that. Well, anyway, the raisins in there are the actual electrons. The rest of the cake is just a positive goo. Now, he was thinking the positive goo would be spread out because it is a big positive charge and the little tiny particles of electrons are just in there. But there wasn't an idea of a positive particle. Now, a competing theory still had the same goo, but it had a much more confined, smaller area of it, more like a planet with the electrons in a ring. But that's our two ideas. Now, to figure out which one of these is the case, one of Dalton's grad students, Ernest Rutherford, this guy, actually decided to take a thin piece of gold and bombard it with alpha particles. Now, alpha particles are about 4 times the mass of a hydrogen atom. So the thought was they would come along here and just go right through this gold. Now, there was a reason that gold was used. Turns out you can get gold really, really thin, and it'll still hold up. That's what gold foil is. And it can be as thin as 3 or 4 atoms thick and still hold its structure. And that is why gold foil was used, because the alpha particles are just going to go right on through. Now, the reason he's expecting them all to go right on through is, if you think about this, this is just a positive goo. The only thing that those alpha particles are likely going to hit are these electrons, and we just said that the alpha particle weighs about 4 AMUs, or 4 times the mass of a hydrogen atom, and yet the electrons are 1/1000. So 4 versus 1/1000, the 4 is just going to blow right through it and keep right on going. But that's not what we see. If we go to this picture, you see how some of these are bouncing straight back? That is, well, we now know the reason that's happening is because there's a nucleus in the middle of the atom. And that's where all the positive is compressed, along with a bunch of neutrons. But the central mass there is just massively huge compared to that 4 AMUs. Matter of fact, on gold has an atomic, 79 protons and, up to, has a total mass of 200 AMUs. So that 4 hitting a 200, it was kind of like hitting a brick wall. Now, when Rutherford first did this, I like this little statement. Just think about this being World War time, so 15-inch shell was something you think about all the time, apparently. But it was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back to hit you. And that's pretty much what they were expecting. No theory had the protons in existence or even condensed. So having all the mass in the central nucleus wasn't even a thought yet. But this kind of proved that's the case. There is a large, dense nucleus in the middle. All right, but that brings us up to the final thing, which was to prove that neutrons were in there. Now, they were long suspected after Rutherford's experiments. And that was mainly because we can't have all those positively charged ions or protons in there without them wanting to repel. So something must be somewhat neutral that holds them together. And that turns out it's the neutrons. It's about the same exact mass of a proton, slightly heavier. But there's at least one for every proton in every stable nuclei. And as we get bigger, there's actually even more neutrons than protons. All right, so we have to modify Dalton's theory. Now, only the first 3 postulates have to be changed. We can't say that we can't just leave one as all matter is composed of atoms. We need to find the atom as the smallest body that retains the unique identity of the element. Because we do know that atoms are made up of protons, neutrons, electrons, and physicists are adding quarks into that. But at least outside of chemistry, or all that's outside of chemistry. In chemistry, we stop at the atom being the smallest because it gives it the unique chemical identity. All right, 2, atoms of one element cannot be converted into atoms of another element in a chemical reaction. Had to add that chemical in there because you can see elements convert from one element into another in nuclear reactions. We might not have direct control over making them any way we want, but we actually can turn most nuclei into another nuclei in a nuclear reaction. All atoms of an element have the same number of protons and electrons, which determines the chemical behavior. Isotopes of an element differ in the number of neutrons, thus the mass number. What we're going to see is there are different versions of atoms with slightly different masses because they have more or less neutrons. Carbon's a good example because it's one we come in contact with. Most carbons have a mass of 12 with their 6 protons, but there are carbon-13s. About 1% of all the carbons on the planet are carbon-13s. And a very, very small fraction are carbon-14s. They are radioactive and decay, and that's how we tell how old things are. All right, so general layout of the atom. Our book uses this nice analogy. I like this analogy to put it in scale perspective to get those numbers in play. If we were to blow up a atom to the size of a football field, in the stands, that is included, the nucleus represents the size of maybe a little blueberry sitting in the middle of the field. So all this empty space is just where the electrons hang out, and all that mass, for the most part, is combined into the nucleus itself. Okay, and what do we see on these actual masses? Oh, I got a formatting issue here, but that's okay. So got the charge of an electron and proton are exactly the opposite. That 1.602 times 10 to the negative 19th coulombs. We roughly can get away with saying a -1 and +1 because that's that unit charge. Their masses, we can kind of get away with still the 1/1000 and 1 and 1 most of the time, but these are a lot more precise. So 0.0055, 1.00727, 1.00866, and these are the actual masses in grams. So you see that the proton and neutron do not weigh the same. Proton is slightly heavier. All right, so when we look at the periodic table, we're going to see atomic numbers. That's the number that's, actually I have a picture of the periodic table here. The atomic number is the number on top of the a symbol. Now the mass number, the next one that's on that page, is not on the periodic table. Mass number is, there is a molecular atomic mass on the periodic table that's close to the average mass number, but that's like, well, in our carbon, we said there was a carbon 12 and there was a carbon 13 and there was a carbon 14. This was 99% of the time. This is 1% of the time, and this is a very small amount of time. When we average those up, we see that the average carbon weighs 12.0107. But that is not the mass. That's not what we're talking about here. Mass number is just a number of protons, a number of neutrons. So for this carbon, this would be 12. This the carbon 13, the mass number is actually 13. It's just a whole number integer. All right, and if an atom's neutral, then the protons and, ooh, that's wrong, and electrons are the same. And I have no idea why I'm pointing out the most common isotope of iodine is 127, but it's there. All right, so chemical symbols. When we look at the periodic table, we're going to see just 1 or 2 letter abbreviations for every atom on the periodic table. If you have an old enough one that has 3-letter abbreviations, and that's what used to happen on elements 103 through 118, they had 3-letter abbreviations that were basically just a representation of their number. They've all been named, and the entire bottom row as of November 2016 has fully named. And let me go to periodic table here real quick so we can see that. So they are fully named. They are hollowed out because every single one of these from Neptunium on have to be made in a nuclear reactor or through a nuclear process. They do not exist in nature. All the hollowed out ones, so even this one here and even right in the middle, 43, need to be made in a nuclear reaction. Okay, so our newest ones are named after the contributing scientists that created it. So Nihonium, Nihon is Japan. Moscovium, Tennesseeine, should have called it Rocky Topium. And Oganession, this is named after the scientist who had a lot of the math behind proving that those things actually existed. Because while they are made, they don't last very long, a few milliseconds at best. So you have to see evidence that they existed to prove that they exist. All right, isotopes are nuclei will have more neutrons or less neutrons than each other, or a varied number of neutrons. Now, if I wanted to figure out how many neutrons a particular atom had, I'm going to do this with this magnesium. Now, to figure out the number of protons, I just need to look on the periodic table and see that magnesium has an atomic number of 12. And the 12, that's right above it on the atomics on this periodic table, right there, that is what we're looking at for the atomic number, which is the number of protons. Now, to get the number of neutrons, we just do subtraction. 24 minus 12 is 12. 25 minus 12 is 13. 26 minus 12 is 14. And if we are dealing with a neutral atom, our electrons and protons are exactly the same. Now, the natural abundance, that needs to be determined outside of this class. So that's something that would be provided. But that's so you can figure out what the actual average mass is. Now, we don't need to actually do that math either, because we can actually look at and figure out what the average mass is. It's right on the periodic table. For magnesium, the average mass is 24.3050 AMUs. Okay, but how that's obtained, we're going to look at it for boron, because it's only got 2 stable isotopes that contribute into it. So turns out boron 10, which is 5 protons and 5 neutrons, if I add up all those masses of those protons and neutrons, and not just the ones from that slide a few pages ago, the 1.007, the 1.008, and add in the binding energy and do all the crazy math you have to do, you get that boron 10 is actually 10.0129 AMUs. Boron 11 is 11.0093 AMUs. You take those numbers and you multiply them by their percents and add those two together, and you get the average of that, or the average of the natural abundances. And that's what you get. That's where we get the atomic mass, which is found on the periodic table. So mass numbers are not, but atomic mass is. It's always right underneath the symbol on our periodic table. Okay, on to chemical formulas. That's an interesting blotch. Okay, went away. All right, so chemical formulas are going to show us how we put atoms together. Now, the molecular formula is by far the simplest way to represent it, but it's almost always not complete enough. Like, for instance, even something as simple as C2H6O, 2 carbons, 6 hydrogens, 1 oxygen, there's 2 ways to put that together. What I mean by 2 ways to put it together, I could put the carbons together, and then the oxygen, and then surround all those with the remaining 6 hydrogens. And I've just made the same molecule I have drawn down below. This is ethanol. Found in gasoline, found in beer, found in liquor. All right. Another way to put it together, I'm going to put the 2 carbons on either side of the oxygen. So the oxygen is going to be in the middle instead. And this has a couple names, but I'm going to go with the one that's more common, dimethyl ethane. Ether, sorry. So dimethyl ether, we find it in 2 things that you might have heard of: carburetor cleaners and sterno. It's the stuff that causes sterno to burn. So sterno, if you're not aware, is like a jelly that you set it on fire and it'll burn. Well, the stuff that burns or helps it burn is dimethyl ether. Now that's similar to diethyl ether. Change this to M and just drop it. Diethyl ether used to be used as an anesthesia. Dimethyl ether would probably have a similar effect, but I have no idea. All right, but both of those have the exact same molecular formula of C2H6O. So sometimes it's better to use what we call a structural formula that splits things up so you can see how they're put together. So see how this was C with 3 hydrogens, CH3, C with 2 hydrogens, CH2, and then OH, OH. This thing would have a structure formula of CH3O, CH3. So you're seeing how it's put together in that formula. Now it draws it out a little bit more, but it's sometimes more beneficial. Now below that we have what we call our Lewis structure. Well, actually that's not quite a Lewis structure. To make this a Lewis structure, it needs to have some lone dots on it. And same as my drawings, I should have those on there. But we'll learn, and we're going to learn how to do those later and add to what you learned in intro. All right. Next to our Lewis structure of ethanol, we have what's more properly called a perspective drawing. Now, the reason it's drawn this way, the wedges are supposed to imply hydrogens coming at you, dashes hydrogens going behind you. So the only thing that's flat on the paper is this H to C to C to H. These H's are both coming out, though the OH and that H are going into the paper. It's supposed to represent a 3-dimensional structure. That's what this picture is. It's actually trying to show you this structure in a 3-dimensional molecule. That's beneficial when we start to look at things like how shape affects molecules, and how the fact that this bond, that bond right there, this bond right here, has a little bit of strain rotating because this O gets closer to this H at some points, and if I stagger it off, if it's over here some, it's a little bit further away. So that's something that factors in later on into chemistry. But right now, we're focused on just that molecular formula, maybe the structural formula. All right. Other things that structural formula can do to us is actually help us figure out the empirical formula. Now, the empirical formula is simply the whole number ratio of the atoms found in a molecule. Now, below my diagrams here, I have acetic acid and I have methyl formate. Now, they both have a formula C2H4O2, C4H2O2. And matter of fact, I could divide each of those numbers by 2 and see that these both have the empirical formula of CH2O. CH2O. And we will find that the empirical formula of CH2O is the empirical formula of all carbohydrates. So glucose, which has a molecular formula of C6H12O6, we could divide all these by 6 and get CH2O. So that empirical formula is actually telling us the nature of the class of compounds, carbohydrates. Now, that's not saying they're all the same. You definitely wouldn't want to put vinegar on your breakfast cereal or in your coffee, although you might. There are people who put sugar in their coffee, which I think is weird. But we use these empirical formulas to figure out the first aspects of a molecule. And we actually can experimentally determine the empirical formula in labs as simple as even ours at the college. Getting the molecular formula is actually doable as well. But to be quite honest, it'd take a little bit more effort to distinguish between acetic acid and methyl formate, because they both have the exact same molecular formula, but their chemical structure is slightly different. Now, fortunately, these two have enough structural difference that they have drastically different chemical properties. You definitely wouldn't mistake one of these for each other. Acetic acid has a very vinegary smell. Methyl formate is going to smell a little bit more, I believe, like Elmer's glue. I think that's what you'd probably compare it to. All right. Structural isomers is just another way of taking the exact same molecule and putting it together in different ways. Or another way of saying that we've taken the same molecule and putting it together this ways. That was what we just saw on this previous slide. These bottom two things are what we're going to call structural isomers. They have the exact same formula, molecular formula, we just put them together differently. Even that ethanol and dimethyl ether are structural isomers. All right. In addition to that, we have spatial isomers. All right, these are kind of odd. All right, so if you look at this molecule and you look at this one, they look like they're just mirror images of each other. Turns out that's all that's different about them. They actually are mirror images of each other. Now, these particular molecules cannot be turned into each other, because if you think about a left-handed glove and a right-handed glove, they're not really interchangeable. These molecules are not interchangeable. So they are both called carbone, but they have that positive or negative in front of them. They have totally different properties. They're both found in nature, but we find them in different aspects. Like the positive one we found in the sides of seeds. The negative one we found in the structure of leaves. But they're both found in nature, just kind of a mirror image of itself. Now, quite often, a lot of stereoisomers have no function in the body. Like, for instance, glucose, which we had up before, it is a stereocenter molecule. Its complete mirror is not biologically active whatsoever. As in, if you were to consume the mirror image of glucose, it'd be almost as beneficial as eating sand. So it'd probably come through the full process of your body and looking almost exactly like it did when it went in, because your body cannot get anything out of the mirror image of glucose. All right, so on to the periodic table. Now, we've talked about the periodic table before, but the biggest reason the periodic table is the way it is, and the reason it's looked at the way it is because this guy, Dmitri Mendeleev. I get a kick out of cut off his statement. But what I was focusing on mostly here was the properties of an element he predicted that would exist. Ecosilicon meant undersilicon, and germanium. See, that was something that Mendeleev did that no one had done before. When he made a periodic table, he didn't put a table of all the elements that were known to exist. He left spaces where he thought some should be, because he thought, okay, there should be something here, we just haven't discovered what it is. And he did that because he saw that there are so many things on the periodic table that had similar properties or similar behaviors. So he made these predictions on what he called ecosilicon. He predicted to have a mass around 72, have a density, have the molar volume. He predicted all these things. And then later on, when germanium was discovered, it was found to be perfectly like that. And if you look at the periodic table, germanium is right underneath silicon. So Mendeleev figured all this out on his periodic table. Now, his periodic table looks drastically different than ours. This is how he came up with it at first. While it has similarities to ours, there are a certain number of differences that we have to figure out what was going on. But modern one has it all arranged in a nice organized fashion. Now, I know it doesn't look organized yet, but we'll see that it is actually organized, very beneficial towards the complete understanding of what's going on in the periodic table. All right, so right now we have a few groups we want to look at. Our main groups are groups 1, 2, 13 through 18. Now, these numbers might be different than what you've seen on previous periodic tables. If you saw some with letter A's up here and B's, ignore that. Those numbers are not acceptable according to the International Standards Committee. So the groups are just 1 through 18 right across. So 1, 2, 3, 4, 5, and then up to 18. And the main group elements are 1, 2, 13, 14, 15, 16, 17, 18, the tall ones. That is what we call the main group elements. The transition elements are the ones we skipped, 3 through 12. These aren't really given group numbers. That's why they're separate. They're going to be called something else. But 3 through 12 are our transition metals. All right, intertransition are the ones down below. The names here come from the first name in the row. And then the other 4 names that are named groups that we need to learn and that we use a lot are the alkali metals, which is group 1, alkaline earth metals, which is group 2, halogens, group 17, and noble gases, group 18. There are other names for other groups on there, but they're not nearly as commonly used as those 4 and these names up here. All right, the other thing to notice on the periodic table, blue things are metals, yellow are nonmetals, green are metalloids, white are unknown. Has to deal with the fact they haven't existed long enough for us to fully get the properties of them. They are probably all metals, though. Even oganessium, which is in the noble gases category, it is probably going to be a metal when they finally attribute it to stuff. All right, so on to our compounds and how we named them. Now, fortunately, many of you had intro, and we will see that we're not going to change that much at all. Molecular compounds or covalent molecules are going to be named pretty much the exact same way as they were. And ionic compounds, nothing you were taught was wrong before, it just wasn't as complete as it needs to be. All right, so on to naming ionic compounds. Now, generally, it is better to say an ionic compound yields by combining cations and anions. In most intro textbooks, we say metals and nonmetals, but it's much more proper to say cations and anions because it needs to be a positively charged species and a negatively charged species. Now, it happens to be that can be metals and nonmetals. Happens a lot. Metals form positive ions easy, nonmetals form negative ions easily. But it doesn't have to be just those. There are some ionic compounds that don't have metals in them at all, but they do have cations and anions. Okay, so for our refresher, oh, I don't want that yet. We'll come back to that. For our refresher, we're going to actually, I'm missing some slides right there. Remind ourselves how we did this from our introductory chemistry rules. So when we name a compound based on its ionic formula, we will always say the name of the metal. And we'll say the name of the nonmetal, but it's not chloride, or not chlorine, it becomes chloride. Change the suffix to an IDE. So sodium and oxygen become sodium oxide. Potassium and bromine, that should be a capital P, become potassium bromide. Cadmium, sulfur, etc., etc. I'm not going to do all these because we are just going to be doing the same thing. The next one is calcium iodide. The one after that is magnesium nitride, cesium fluoride, calcium phosphide, lithium chloride, and aluminum carbide. You just change the suffix to IDE, and there is nothing changed there. So if it's a metal and non-metal, you name it like that. Now, there is an exception to this rule. Turns out some of our metals have more than one charge states. Matter of fact, every single transition metal does. Now, this chart shows the common ions, but it turns out all these yellowish colored ones have multiple charges except for those three. So what I mean by that, it turns out copper has a +1 and +2 ion that happen all the time. So therefore, there is two different forms of copper chloride. There is a copper, if this is a +2, it would need 2 chlorines with it. Copper 1, chloride 1. And copper 2 chloride is a blue crystal. When it gets a little bit moisture around it, it's brown otherwise. Copper 1 chloride is a white crystal. Totally distinguished molecules. They are not exchangeable. I cannot, turn this one into this one. And they have totally different properties. This one, copper CuCl2 is totally soluble in water. CuCl is not. So drastically different chemical properties. All right, so when we actually have a nonmetal like that, what we're going to have to do, or when we have a metal like that, what we're going to need to do is include the charge. We're going to do that for any time there is a metal that has more than one charge state. So back up to that periodic table, every single thing in that transition metal except for these 4, or these 3. Matter of fact, the fixed charges are those 2 rows, those 3, and aluminum. Every single other metal or blue thing on our periodic table needs to have a charge listed when you come up with a chemical structure. So let's see what that looks like. So, not that example, this one. So I have copper with oxygen, and I have copper with oxygen. I got 2 back-to-back, we're 2 different ones. What we need to do is figure out what the charge of the copper would have to be to put it with that oxygen. All right, oxygens are always -2 charges. This copper must be a +2. So we're going to call it copper 2 in Roman numerals oxide. And if we do the same thing here, this is -2. Therefore, each one of these coppers must be +1. So this one is copper 1 oxide. Let's see if we can do these. So the oxygen's -2. There's 3 of them. These would need to be +3. Iron 3 oxide. Give me a moment to think of that one. It is iron 2 oxide. All right, now these last 3 are kind of to trick you. So I got silver, cadmium, and zinc. I want you to remember back on this, they have fixed charges. It's always +1, it's always +2, it's always +2. And because of that, they don't get Roman numerals. This is just silver chloride. And this is cadmium chloride. And this is zinc oxide. No Roman numerals on those. So all your transition metals get Roman numerals except for those 3 and aluminum and even some of those other metals. All right, so this is a nice little summary. Now, it's out of an old book, which is why these group numbers are wrong. And this shouldn't say 3 to, how about, I don't like those numbers at all. 1, group 1, and group 2, and zinc, silver, cadmium, and aluminum. And this over here is all others. And if it's any of those others, it gets a Roman numeral saying what the charge is. If it's in group 1 or group 2 or zinc, silver, cadmium, or aluminum, you just put down their names. And now we're adding ammonia. If you remember, ammonia or ammonium is a polyatomic ion. We haven't added those to our list, but we're following the same rules as we introduced in intro. If I have a polyatomic ion, I'm using its name intact in the molecule. But ammonium is the only positive species we have, which is why it's included over here for metals. There's a cation that doesn't have a metal in it. Now, nonmetals don't have any need for Roman numerals because all of your nonmetals that are just atoms are just going to have their charges based on where they're at in the periodic table, and all the polyatomics will have their charges based on which polyatomic ion it is. So the only thing we've added new to this is figuring out how to add our transition metals into it. And we're going to add to our polyatomic ions. Now, this polyatomic ion table is right out of your book, but it's not as complete as it needs to be. So there's a couple things they left out. For instance, along with chlorate, there is also bromate. Bromate. And if you imagine chlorate with ClO3, bromate must be BrO3. And one of my favorite names, it sounds like I made it up, iodate. But iodate is IO3. Now, there's not really a fluoridate, so we don't have all the polyatomic ions. Now, bromate and iodate do the exact same as chlorate, so there is a perbromate, and there is a bromite, and there is a hyperbromite. And they have similar ideas, where they're just changing the number of oxygens in there. All right, but you'll want to get comfortable with this chart. Just from the sheer amount of time we're going to use it, you're probably going to end up having most of these memorized, but it is to your benefit to memorize them. Now, some of them are provided on the periodic table I give you for the tests, but it's not all of them. So I do encourage you to look at the periodic table on Canvas to see what is provided, so you can learn the rest or how to derive the rest. All right, and naming those. These are actually relatively simple in the sense that we don't need to change the suffix ever. You just have to know what the polyatomic ion is. So this first one, I got potassium and C2H3O2 is acetate. Ammonium, chlorine becomes chloride. Sodium. HCO3 could be hydrogen carbonate or bicarbonate. Calcium sulfate. Aluminum carbonate. And magnesium phosphate. And none of those need Roman numerals because none of these are transition elements. Okay, couple more examples just to put it in perspective. We're going to at first decide if we need Roman numerals. All right, with iron, and we do that by looking at the periodic table. We see that iron is a transition metal. So we are going to have iron with a Roman numeral with it. And sulfur, being in group 16, is a negatively 2 charged species. So iron must be an iron 3. So this must be iron 3 sulfide. Copper with selenium. Selenium is also in group 16, so it's also -2. So this is copper 2 selenide. We have gallium with nitrogen. Nitrogen's a -3. Gallium 3 nitride. Cr is chromium. It's with 3 chlorine, so it's chromium 3 chloride. And our last one, titanium. It's in group 13. It will need a Roman numeral. Sulfate's a -2. So this is, I said group 13. Titanium's in group 4. Titanium 3 sulfide. Ooh, a lot of Roman numeral possibilities, huh? All right. Molecular compounds, we're not really changing anything we did here. Most often occurs between 2 nonmetals, 2 or more, and you will use prefixes to say how many there are. And these aren't really changing any. We sometimes leave out mono. About the only time we do specify it when it's darn important. Like we often actually mention carbon monoxide because it's a dangerously deadly compound compared to carbon dioxide. So mono doesn't get used very often, but let's see if we can do this. SO2, sulfur dioxide. BCl3, bromine trichloride. All right, on to naming acids. Now, we only really have 2 different naming categories we fit things into. Binary acids, which is hydrogen attached to a nonmetal. Doesn't matter what the nonmetal is, it's just a hydrogen attached to a nonmetal. Now, if it's dissolved in water, that's going to create a minor acid. It's either going to be a strong or weak, but all the nonmetals dissolved with hydrogen make somewhat of a weak acid, as long as it dissolves in water. So HCl dissolved in water. If I want to name this, I'm going to change hydrogen to hydro. Instead of saying chloride, chloric, and then add the word acid. So hydro sulfuric acid. Sometimes see hydrosulfic. So the UR is dropped and it just goes to SULFIC acid. But hydrosulfuric is more common, and that is an R. And this last one is trying to throw you off, and so you'd say hydroiodic acid, but it's not hydroiodic acid because it's a gas. As a gas, it's just hydrogen iodide. If it said aqueous, I'll put this up here. I can't write at the bottom too well. If it was aqueous, it would be hydroiodic acid. All right. Now, our other acids are oxoacids. These are acids where we put H with a polyatomic ion that has oxygen in it. All right, that's pretty much all of our polyatomic ions for the most part. So if you take any of the polyatomic ions that we have and put H in it, H with it, we've made an acid, an oxoacid. And what we're going to do is look at the name of the polyatomic ion and change its suffix to ic if it ends in ate, or us if it ends in ite, and then put acid there. There is no use of hydro. So since SO4 is just the sulfate ion, this whole thing is sulfuric acid, which is totally different than hydrosulfuric acid. Hydrosulfuric acid is just H2S. Sulfuric acid is SO4 with the H2. All right, H2SO3, since this is sulfite, this becomes sulfurous acid. HC2H3O2, that is acetate. This becomes acetic acid. And then NO2, nitrite, nitrous acid. All right, before we're done with this chapter, I'm going to look at one more potential acid thing. I'm going to go back to our polyatomic ions. If you look here, all of our polyatomic ions on this table had H in it, except for ammonia, which I can't really combine with H pluses and make acids because it's already positive, and CN. Turns out HCN is an acid, but we name it as if it's following binary acid rules. So CN is the cyanide ion. So we're going to say hydrocyan. Let me fix that. Cyanic acid. It's the only one that really does anything. And if you want to scare people, HOH, otherwise known as water, hydroxide, right? Just hydroxide. We could probably make up a weird name. Hydroxyic acid. I still like dihydromonoxide a little bit more. Sounds kind of scary. Dihydrogen monoxide. All right, that finishes up chapter 2, and we are ready to move on.